Hi, grade 6 students. This is day 14, lesson 9-3, problems 9 through 29, the odds. Today's lesson is about something called the fundamental counting principle. Before we get into it, let's take a look at something we already have looked at, tree diagrams. Let's imagine we have a situation in which somebody has 4 pairs of socks. The socks are green, yellow, orange, and purple. They also have 3 pairs of shoes. The shoes are white, blue, and red. And somebody says, how many different ways could somebody cover their feet using these socks and these shoes that are available? Well, one way you could do it is with a tree diagram. This represents the socks, green, yellow, orange, and purple. And these letters represent the shoes, white, blue, and red. And you'll notice over here, when we figure out the amount of outcomes, there ends up being 12 different ways of using these socks and shoes. And it works pretty well in a circumstance like this. But what if the numbers you have are bigger than 4 pairs of socks and 3 pairs of shoes? What if, say, for example, somebody had 12 different pairs of socks? And what if they had 7 pairs of shoes? Then suddenly the tree diagram that you would draw for something like this would be incredibly hard and difficult and big to create. So that's what today's lesson is about. How do you do this with larger numbers of events that might be happening? Please take a look at page 378 and 379, read it carefully, and then come back and we're going to discuss some example problems. Okay, you're back. So hopefully you understand that in this particular circumstance we could do a tree diagram, but it would be huge. Your textbook suggests something called the fundamental counting principle, where it says that you can take these 2 numbers, multiply them together, and that is a fast way of finding out how many outcomes you would have created had you drawn a tree diagram for this circumstance. In this case, there are 84 different ways that one could wear the socks and the shoes in this person's closet and dresser drawer. Let's try some other examples of this type of problem. Let's imagine that somebody had 4 different kinds of shirts, and they had 3 different pairs of shorts, and they had 2 different pairs of shoes. How many different outfits could they create out of this? Well, you could draw a tree diagram. What would the tree diagram look like? Well, let's start first with the shirts. We could talk about shirt A, B, C, and D. And then we could talk about the shorts. How about pair of shorts 1, 2, and 3? Boy, this is starting to get a little complicated. What's going to happen in that next row? And then we have 2 different pairs of shoes. How am I going to represent that? How about a Roman numeral 1 and a Roman numeral 2 to represent the shoes? Do you notice how complicated this tree diagram is getting? The fundamental counting principle says you can figure out the amount of outcomes, or in this case, the amount of outfits, simply by multiplying 4 times 3 times 2, which in this case would be 24 different outfits. Let's try another example. Let's imagine that an orchestra has 1 opening for a violinist, 1 opening for a cellist, and 1 opening for an oboist. 3 musicians are trying out for violin. 3 for violin. And 5 musicians are trying out for the cello. And 3 people are trying out for the oboe. In how many different ways could the orchestra leader fill these positions? Well, again, you could create a tree diagram, but that's going to get pretty complicated. Let's imagine that A, B, and C represent the 3 violinists that are trying out for the orchestra. And then let's imagine that 1, 2, 3, 4, and 5 represent the 5 different people that are trying out for the cello position. And then we're going to use small letters, A, B, and C, to represent the 3 people trying out for the oboe position. Do you notice what's happening? I am definitely running out of room. I would definitely need a much bigger whiteboard to finish this. A faster way of doing it, using the fundamental counting principle, 3 times 5 times 3 should give me 45 different ways in which the person can create this new situation of adding 3 people to its orchestra. Now let's look at the guided practice on the bottom of 379. We're going to go through all of those problems there. Number 5 rather, use the fundamental counting principle to find the total number of outcomes in each situation. Tossing a quarter, a dime, and a nickel. A quarter, a dime, and a nickel. Well, let's think about these individually. How many different ways can you toss a quarter? 2. How many different ways can you toss a dime? 2. How many different ways can you toss a nickel? 2. Using the fundamental counting principle, we get 8 different ways in which those 3 coins could be tossed. Is this a problem where we could have easily done this with a tree diagram? Yes, but the fundamental counting principle also works. Let's look at number 6. Choosing scrambled, sunny side up, or poached eggs with bacon, sausage, and milk, orange juice, or apple juice. Well, at first glance, this problem might seem a little complicated, but think about it in terms of this way. How many different ways are we preparing the eggs? 3. How many different types of meat are we thinking about eating? 2. And how many different drinks are they talking about? 3. So when we talk about the eggs, it's 3 ways. The meats are 2 different versions of meat, and the drinks are 3 different versions of the drinks. Therefore, 3 times 2 times 3 gives us 18 different ways that you could create a breakfast in problem 6. Let's try number 7. Choosing a card from 20 different cards and then spinning the spinner that's at the right. Well, if there's 20 cards, that must be 20 different possibilities. The spinner at the right has 3 different possibilities. Using the fundamental counting principle, we get an answer of 60. Let's try number 8. If Opal, Jacob, Luanda, Tyrone, and Erica have an equal chance of being an officer of student council, what is the probability that Luanda will be an officer? This one's a little bit different. Up until this point, we've only been talking about figuring out how many possible outcomes there are. Now, all of a sudden, they put that word probability into the problem. Remember, probability is favorable outcomes over all of the outcomes. Let's first figure out how many different ways that those individuals can become an officer in student council. Well, there's 1, 2, 3, 4, 5 different students, right? Opal, Jacob, Luanda, Tyrone, and Erica. And if Luanda wants to be an officer, she's got to be picked. And that would be a favorable situation. Therefore, for problem 8, the probability of Luanda being an officer, remember, probability is favorable over all of the outcomes, would be 1 out of 5 in this case. Turn the page. Let's take a look at some of the even numbered problems on the next page. Number 10, choosing a number from 1 to 20 and a color from 7 different colors. Well, using the fundamental counting principle here, we think about 20 different cards, that's 20 outcomes. We think about 7 colors, that's 7 outcomes. Fundamental counting principle says multiply them together, we get an answer of 140. Let's move on to number 12. Choosing iced tea in regular raspberry, lemon, or peach flavors. How many different iced teas is that? Regular raspberry, lemon, or peach flavors. So in problem 12, in the iced tea area, we're talking about 4 different varieties. And then it says sweetened or unsweetened. Oh, okay. So we're adding sweetener or we're not adding sweetener. And there's 2 different ways we can do that. We can either add it or not add it. And then it says putting it in a glass or a plastic container. Well, that's the choice of glass or plastic. That's 2 different ways. So fundamental counting principle says our answer is 16 different ways. How about number 14, choosing a 4-digit personal identification numbers if the digits cannot be repeated. That's important. If the digits cannot be repeated. Okay, 4 different combination number. Like, let's say your combination number would be 5271. That would be a 4-digit password or combination number. But it can't be something like 5541 because I repeated the 5, didn't I? So, how many different possibilities could there be in this first slot? That would be 10. Once we use one of the numbers, here's where it gets a little tricky. We're only going to have 9 available for the second slot because we've already used one. And when we get to the third slot, we're only going to have 8 numbers available for that slot. And finally, something happened. Oh, there we go. And finally, for the last slot, we're only going to have 7 numbers yet because we've used 3 of them in the first 3 slots. We need to take those numbers and multiply them together. Oh boy, 10 times 9 is 90. 90 times 8 is 720. 720 times 7 is 0, 14, 1. I get 5,040 ways. 5,040 ways. Where did I get 10 numbers to choose from? Well, think about it in this sense. You got the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 that could be used in that first slot. That's a total of 10 numbers. So that's problem 14. Let's try number 18. Number 18 says, how many outcomes are possible if you toss each of the following? Number 18 says, how many outcomes are there if you toss 2 coins? Well, on the first coin, there's 2 outcomes, and on the second coin, there's 2 outcomes. So that must mean that there's 4 different ways that you can toss those coins. How about number 20? Number 20 says n amount of coins. What in the world do they mean by that? N amount of coins. Well, n is a variable representing any possible number. What's happening when we do this kind of work here and we're talking about coins that we're tossing? Well, if I talk about 1 coin, that has 2 possibilities, right? If I have 2 coins, we already said that that's 4 possibilities. 3 coins, that would be, that'd be 8 possibilities because that would be 2 times 2 times 2. this is 2 times 2, and this is just plain 2. 4 coins, well, that would be 16 because it's 2 times 2 times 2 times 2, right? 4 different coins, each one having 2 possibilities. What's happening here? Well, this is really 2 to the first power. This is really 2 to the second, and this is really 2 to the third, and this is really 2 to the fourth, right? And so in this situation, the answer is 2 to the nth power. Because notice, with 1 coin, it's 2 to the first. With 2 coins, it's 2 to the second. With 3 coins, it's 2 to the third. With 4 coins, it's 2 to the fourth. So with n amount of coins, it'd be 2 to the nth power. So that's the answer for problem 20. Okay, hope you have an understanding of this. Give me a call if you're stuck. Thank you, and have a good day.